Niels Henrik David Bohr was born on October 7, 1885, in Copenhagen, Denmark, into a family that valued intellectual pursuit and scientific inquiry. His father, Christian Bohr, was a renowned professor of physiology at the University of Copenhagen, which ensured that Niels grew up in an environment deeply embedded in academia. This scholarly atmosphere shaped his early outlook on education and science, nurturing a curiosity that would come to define his later work. The Bohr household, marked by open discussion and a commitment to learning, laid the foundation for Niels's rigorous intellectual development. Bohr's mother, Ellen Adler Bohr, belonged to a prominent Danish Jewish family with a tradition of philanthropy and cultural engagement. The combined influence of his father's scientific rigor and his mother's cultural sensibilities contributed to Bohr's well-rounded upbringing. From an early age, Bohr exhibited a profound interest in mathematics and physics, subjects that would later form the core of his scientific career. Despite the privileged environment, Bohr's upbringing was not devoid of challenges. The expectations for academic excellence were high, and he responded by dedicating himself to study and intellectual growth. Bohr attended the Gammelholm Latin School in Copenhagen, where he excelled academically. His education there was classical in nature, emphasizing languages and humanities alongside the sciences. This broad educational foundation equipped Bohr with the ability to think critically and communicate effectively, skills that would become crucial in his scientific collaborations and philosophical reflections. His success at school allowed him to gain admission to the University of Copenhagen in 1903 at the age of 18, marking the beginning of his formal scientific training. At the university, Bohr initially focused on physics and mathematics, fields in which he showed exceptional talent. Under the mentorship of professors such as Christian Christensen and C.J.J. Sommerfeld, Bohr deepened his understanding of contemporary physics. Sommerfeld, a prominent physicist based in Germany, would later play an indirect but important role in Bohr's development by influencing the emerging quantum theory. During these years, Bohr cultivated an analytical mindset and a methodical approach to problem solving, attributes that distinguished his early research. In 1909, Bohr graduated with a degree in physics, presenting a thesis on the electron theory of metals. His early academic work displayed a strong grasp of classical physics, but also a curiosity about emerging anomalies that classical theories could not explain. This tension between established scientific paradigms and new experimental evidence would become a defining feature of Bohr's career. Upon graduation, Bohr secured a position as an assistant to J.J. Thomson at the Cavendish Laboratory in Cambridge, England, providing him his first exposure to international scientific communities. Bohr's time at the Cavendish Laboratory was brief but formative. There, he interacted with some of the leading physicists of the time and encountered cutting-edge experimental techniques. Despite these advantages, Bohr found the research environment somewhat rigid, and he soon moved on to continue his studies in continental Europe. In 1911, he traveled to the University of Manchester to work under Ernest Rutherford, whose nuclear model of the atom was gaining traction. This period was critical, as it exposed Bohr to the nucleus-centric view of atomic structure and inspired his subsequent theoretical innovations. The year 1912 marked a pivotal moment in Bohr's early scientific development when he was awarded a Danish government scholarship to study abroad. He chose to study in Germany, a center of theoretical physics, and enrolled at the University of Göttingen. There, Bohr worked under Max Born, whose work on atomic mechanics was influential in the early development of quantum theory. Göttingen's intellectually stimulating environment allowed Bohr to engage with contemporary debates on the nature of atoms and radiation, reinforcing his commitment to addressing unresolved scientific questions. Bohr's doctoral thesis, completed in 1911, addressed the electron theory of metals, but did not yet reflect the revolutionary ideas he would soon propose. However, his subsequent research during his time with Rutherford and Bohr set the stage for his breakthroughs in atomic physics. This early period of education and study was characterized by a careful absorption of classical physics, an exposure to emerging experimental discoveries, and a growing awareness of the limitations inherent in existing theories. Niels Bohr's early scientific endeavors were profoundly shaped by the intellectual currents and leading figures of physics in the early 20th century. After completing his doctoral degree, Bohr's quest for a deeper understanding of atomic structure led him into contact with pioneers of experimental and theoretical physics, whose insights would shape his own groundbreaking ideas. This period of initial scientific work was marked by intense exploration and cross-pollination of ideas in an era when classical physics was being challenged by emerging quantum concepts. One of the most significant influences on Bohr during this period was Ernest Rutherford, who had recently proposed the nuclear model of the atom, placing a dense, positively charged nucleus at the center of a cloud of orbiting electrons. Bohr joined Rutherford's laboratory at the University of Manchester in 1911, immersing himself in the forefront of atomic research. Rutherford's model, though revolutionary, could not fully explain the stability of atoms or the discrete spectral lines observed in experiments, problems that Bohr would soon address with his own theoretical innovations. Bohr's interaction with Rutherford was not just scientific, but also pedagogical, as Rutherford encouraged his young protege to question assumptions and pursue novel explanations. This environment nurtured Bohr's willingness to integrate new physics ideas, including the nascent quantum hypotheses introduced by Max Planck and Albert Einstein. The fusion of Rutherford's experimental insights with quantum theory became a hallmark of Bohr's work, enabling him to develop models that bridged empirical evidence and theoretical interpretation. In addition to Rutherford, Bohr was deeply influenced by Max Planck's quantum hypothesis, which postulated that energy was emitted in discrete quanta rather than continuously. This idea, initially proposed to explain blackbody radiation, challenged the foundational assumptions of classical physics. Bohr's appreciation for Planck's work grew as he recognized its potential to resolve anomalies in atomic spectra, motivating him to incorporate quantum principles into his atomic models. Another key figure impacting Bohr's early work was Arnold Sommerfeld, whose extension of the Bohr atomic model introduced elliptical orbits and relativistic corrections, refining the theoretical framework. Though Bohr initially developed his ideas independently, Sommerfeld's contributions provided a more comprehensive understanding of atomic behavior, illustrating the collaborative nature of scientific progress during this period. Bohr's engagement with Sommerfeld's work exemplified his openness to interdisciplinary dialogue and his commitment to evolving his theories in light of new evidence. Bohr's formative years also involved rigorous engagement with the mathematical formalism required to describe atomic phenomena. His background in mathematics was essential in developing quantitative models that could predict spectral lines with precision. This mathematical rigor distinguished Bohr from some of his contemporaries who relied more heavily on qualitative descriptions. By emphasizing calculable predictions, Bohr helped transition atomic physics from speculative theory toward a more exact science. During this time, Bohr also faced the challenge of reconciling the apparent contradictions between classical mechanics and the emerging quantum ideas. He recognized that the electron's behavior could not be fully explained by Newtonian physics, yet quantum theory was still in its infancy and lacked a complete framework. This tension motivated Bohr to propose radical assumptions, such as the quantization of angular momentum, which broke from traditional physics but offered explanatory power. Bohr's initial scientific papers published between 1912 and 1913 laid the foundation for his later atomic model. These works combined experimental data, particularly from spectroscopy, with theoretical assumptions inspired by quantum principles. By analyzing the spectral lines of hydrogen, Bohr identified patterns that classical physics could not explain, setting the stage for his revolutionary hypothesis that electrons occupy specific, quantized orbits around the nucleus. Beyond his scientific work, this period was also marked by Bohr's growing reputation within the international physics community. He attended conferences and engaged in correspondence with other physicists, exchanging ideas that would refine his understanding and clarify the implications of quantum theory. These interactions not only enriched Bohr's work, but also helped disseminate his ideas to a wider audience, establishing him as a leading figure in the evolving field of atomic physics. The introduction of the Bohr model in 1913 marked a defining moment not only in Niels Bohr's career, but also in the history of physics. This model fundamentally altered the scientific understanding of atomic structure by proposing a new framework that combined classical mechanics with emerging quantum ideas. At its core, the Bohr model sought to explain the discrete spectral lines observed in hydrogen and other elements, an issue that had long puzzled physicists and defied explanation through classical theory alone. Bohr's approach was revolutionary in that it introduced the concept of quantized electron orbits around the atomic nucleus. He postulated that electrons could occupy only certain allowed orbits, each with a fixed energy level, and that electrons would not emit radiation while remaining in these stable orbits. This assumption directly contradicted classical electrodynamics, which predicted that accelerating electrons should continuously radiate energy and spiral into the nucleus, leading to atomic collapse. By restricting electron motion to specific orbits, Bohr circumvented this problem and explained atomic stability. A central element of the Bohr model was the quantization of angular momentum, which Bohr expressed mathematically as the electron's angular momentum being an integer multiple of Planck's constant divided by 2 pi. This discrete quantization condition was unprecedented in classical physics and introduced a new rule governing atomic behavior. Through this condition, Bohr derived the radii of allowed orbits and the corresponding energy levels, providing a theoretical basis for the spectral lines observed experimentally. The model successfully accounted for the Rydberg formula, which described the wavelengths of hydrogen's emission lines. Prior to Bohr's work, the Rydberg formula was empirical, lacking a theoretical foundation. Bohr's model explained the formula by linking it to electron transitions between quantized energy levels, where the emission or absorption of photons corresponded to energy differences between these levels. This marked a major achievement, as it connected atomic structure directly with spectral phenomena. Despite its successes, the Bohr model was limited in scope. It worked best for hydrogen-like atoms with a single electron and could not fully explain the spectra of more complex atoms. Moreover, it retained many classical mechanics elements, such as defined electron orbits, which would later be challenged by the development of quantum mechanics. Nevertheless, the Bohr model represented a crucial stepping stone that bridged classical and modern physics. Bohr's model also introduced the notion of electron transitions as discrete jumps rather than continuous changes, a concept that was initially difficult for the physics community to accept. These quantum jumps implied that an electron could instantaneously move between energy levels, emitting or absorbing photons of specific energies. This idea laid the groundwork for the probabilistic nature of later quantum theory, even though Bohr himself initially viewed these jumps as physically real events. The publication of Bohr's atomic theory was met with both enthusiasm and skepticism. Many physicists recognized its explanatory power, especially in addressing the shortcomings of Rutherford's nuclear atom. Others were hesitant to abandon classical intuitions or to accept the seemingly ad hoc quantization rules. Over time, experimental verification, such as the observation of spectral lines matching Bohr's predictions, helped secure its acceptance. Importantly, Bohr's model sparked further research and theoretical refinement. Scientists like Arnold Sommerfeld extended the model by incorporating elliptical orbits and relativistic effects, improving agreement with observed spectral data. These enhancements demonstrated that the Bohr model was a dynamic framework, open to adaptation and expansion as new data emerged. The impact of the Bohr model extended beyond physics, influencing chemistry and other sciences by providing a clearer picture of atomic behavior. It helped explain chemical bonding and the periodic table structure by linking electron configurations to energy levels. This cross-disciplinary influence highlighted the model's broad scientific significance and Bohr's role in fostering interdisciplinary understanding. The early 20th century witnessed a profound upheaval in the understanding of physical reality, largely driven by the development of quantum theory. Niels Bohr was at the forefront of this revolution, not only advancing the theoretical framework, but also grappling with the philosophical implications of the new physics. His work extended beyond mathematical models into the conceptual foundations of how nature could be understood at the atomic and subatomic levels. Following his introduction of the Bohr model, Bohr delved deeper into the emerging quantum theory, which challenged the classical notions of determinism and continuity. Quantum phenomena revealed that particles like electrons and photons sometimes behaved like waves, and at other times like particles, a duality that confounded conventional descriptions. Bohr recognized that this wave-particle duality was not just a curiosity, but a fundamental feature of quantum entities. In seeking to clarify this paradox, Bohr proposed the principle of complementarity, which became one of his most significant contributions. This principle asserted that the wave and particle aspects of quantum objects were complementary descriptions, both necessary to fully understand quantum phenomena, but mutually exclusive in terms of observation. In other words, depending on the experimental arrangement, an electron could exhibit wave-like interference patterns or behave as a discrete particle, but never both simultaneously. Complementarity challenged the classical ideal that a single, objective description of reality could suffice. Instead, Bohr suggested that the nature of quantum objects was inherently linked to the conditions under which they were observed. This idea introduced a radical shift from viewing scientific descriptions as absolute representations of reality to understanding them as contextual and dependent on measurement. Bohr's philosophical stance drew heavily from the practical demands of quantum mechanics and the limitations imposed by the uncertainty principle, formulated by Werner Heisenberg. The uncertainty principle stated that certain pairs of physical properties, such as position and momentum, cannot be simultaneously measured with arbitrary precision. Bohr interpreted this as a reflection of nature's fundamental limits, reinforcing his complementarity concept and emphasizing the inseparability of the observer and the observed. In addition to its conceptual importance, complementarity influenced the design and interpretation of experiments. Bohr argued that the classical language of physics was indispensable for describing measurement apparatus and results, even if it failed to capture the full quantum reality. This insistence on classical terms was pragmatic, ensuring communication and reproducibility in science, yet it acknowledged a profound epistemological boundary. Bohr's ideas also provoked extensive debate within the physics community, especially with Albert Einstein, who famously resisted the probabilistic and contextual aspects of quantum mechanics. Their correspondence and public exchanges, known as the Bohr-Einstein debates, explored the philosophical foundations of quantum theory and the nature of reality itself. While Einstein sought a deterministic and complete description, Bohr defended the probabilistic interpretation and the role of complementarity. The complementarity principle further influenced Bohr's efforts to unify physical theories and reconcile quantum mechanics with relativity. Although a complete unification remained elusive, Bohr's insights underscored the necessity of developing conceptual frameworks capable of accommodating apparently contradictory phenomena. His work foreshadowed later developments in quantum field theory and the philosophy of science. Bohr's approach to quantum theory was not only scientific, but also deeply reflective, bridging physics and philosophy. He engaged with broader intellectual currents, including epistemology and the limits of human knowledge. By emphasizing the interplay between observation, measurement, and reality, Bohr contributed to a more nuanced understanding of science as a human endeavor shaped by both empirical data and conceptual frameworks. The Copenhagen interpretation emerged as one of the most influential and widely discussed frameworks for understanding quantum mechanics in the 1920s and 1930s. Although the term was not coined by Niels Bohr himself, it became closely associated with his ideas and the scientific environment he cultivated at the University of Copenhagen. This interpretation synthesized the evolving quantum theories into a coherent philosophical and practical approach to atomic and subatomic phenomena. Central to the Copenhagen interpretation was the idea that quantum mechanics does not provide a deterministic description of individual events, but rather predicts probabilities of different outcomes. This probabilistic nature marked a significant departure from classical physics, where the behavior of systems could, in principle, be predicted with certainty if initial conditions were known. Bohr, along with his collaborators, emphasized that the quantum formalism was complete in its statistical predictions, though it eschewed a definitive account of reality independent of measurement. The interpretation also stressed the role of measurement as a fundamental process. Unlike classical physics, where observation could be considered passive, the Copenhagen view held that measurement irreversibly affects the system being observed. This concept introduced an inherent limit to what can be known about quantum systems, underscoring the inseparability of the observer and the observed. Bohr's insistence on this principle shaped experimental design and theoretical inquiry. A key element of the Copenhagen interpretation was the use of classical physics language to describe measurement apparatus and outcomes. Bohr argued that, despite the novel behavior of quantum systems, experimental results had to be communicated in classical terms to be meaningful and reproducible. This pragmatic stance maintained continuity with scientific tradition and allowed the interpretation to function as a bridge between the old and new physics. The development of the Copenhagen interpretation was not the work of Bohr alone. His colleagues, including Werner Heisenberg, Wolfgang Pauli, and Max Born, contributed essential mathematical formalisms and conceptual clarifications. Heisenberg's uncertainty principle, for instance, provided a quantitative expression of the limits on simultaneous knowledge of certain pairs of observables. Pauli's exclusion principle and Born's probabilistic interpretation of the wave function further enriched the framework. Despite its explanatory power, the Copenhagen interpretation faced significant philosophical and scientific criticism. Many physicists, including Albert Einstein, Erwin Schrödinger, and Louis de Broglie, expressed discomfort with its apparent abandonment of objective reality and determinism. Einstein famously remarked, "God does not play dice. encapsulating his resistance to the idea that chance and probability were fundamental rather than indicative of incomplete knowledge. The debate over the Copenhagen interpretation extended beyond physics to touch on broader philosophical questions about realism, causality, and the nature of knowledge. Bohr defended the interpretation not only on scientific grounds, but also as a necessary revision of how humans could comprehend the quantum world. He argued that classical concepts, while insufficient to fully describe quantum phenomena, were indispensable as a language for scientific communication and practical measurement. The influence of the Copenhagen interpretation was also institutional. Bohr's Institute in Copenhagen became a hub for physicists from around the world, fostering collaboration, discussion, and the dissemination of quantum ideas. This intellectual environment helped consolidate the interpretation's dominance during the mid-20th century and shape the training of generations of physicists. Over time, alternative interpretations of quantum mechanics have been proposed, including the many worlds interpretation, pilot wave theory, and objective collapse models. However, the Copenhagen interpretation remains foundational in physics education and experimental practice. Its emphasis on complementarity, measurement, and probability continues to inform how quantum mechanics is understood and applied. The outbreak of World War II in 1939 drastically altered the trajectory of many scientific careers, including that of Niels Bohr. As a prominent physicist of Jewish descent in Nazi-occupied Europe, Bohr faced immediate personal and professional dangers. His scientific pursuits took on urgent geopolitical significance, particularly as the potential for atomic energy to be harnessed as a weapon became increasingly apparent. Bohr's initial response to the war involved attempts to safeguard Danish scientific institutions and colleagues. When Germany invaded Denmark in April 1940, Bohr took steps to protect his institute and its research while navigating the complexities of occupation. He was deeply concerned about the ethical implications of nuclear research, especially in light of Nazi Germany's potential development of atomic weapons. In 1943, the situation in Denmark became perilous for Bohr due to his Jewish heritage. With help from the Danish resistance and British intelligence, he managed a dramatic escape to Sweden and subsequently to the United Kingdom. This escape was a pivotal moment, enabling Bohr to join the Allied scientific efforts and contribute directly to the development of nuclear technology in the West. Bohr's arrival in the United Kingdom connected him with the scientific teams involved in the Allied atomic bomb project, known as the Manhattan Project. Although initially unfamiliar with the project's full scope, Bohr quickly became an important advisor due to his extensive knowledge of nuclear physics and his insight into the ethical dimensions of nuclear weapons development. Recognizing the international stakes, Bohr advocated for open scientific communication among the Allies and urged caution in the use of atomic weapons. He believed that nuclear technology should not be monopolized or used recklessly, anticipating the profound consequences such weapons would have on humanity. This perspective made him a unique figure within the Manhattan Project, blending scientific expertise with moral responsibility. During his time in the United States, Bohr worked alongside leading physicists such as Robert Oppenheimer and Enrico Fermi. Although his involvement in the project's technical aspects was limited by security restrictions and his age, his conceptual insights helped shape discussions about nuclear chain reactions and reactor design. Bohr's presence symbolized a continuity between pre-war European physics and the wartime American scientific mobilization. Bohr also played a crucial role in promoting post-war international cooperation. He advocated for a framework that would ensure atomic energy was used for peaceful purposes and proposed that scientists from all nations collaborate to prevent nuclear proliferation. His vision anticipated later efforts to establish international control over nuclear technology through organizations such as the International Atomic Energy Agency, IEA. The complexities of Bohr's wartime activities were not without controversy. His efforts to communicate with Soviet scientists, as well as his calls for openness, raised concerns among some American officials about security and espionage. Nevertheless, Bohr's commitment to transparency and international dialogue underscored his belief in science as a universal human endeavor transcending political boundaries. Bohr's experience during World War II left a lasting impact on his post-war career. He emerged as a leading advocate for arms control and nuclear disarmament, using his stature to influence policy debates and public opinion. His warnings about the dangers of nuclear weapons resonated globally, positioning him as a moral authority in addition to a scientific pioneer. Following the end of World War II, Niels Bohr returned to Copenhagen with a renewed sense of purpose. The devastation wrought by the atomic bombings of Hiroshima and Nagasaki had underscored the urgent need for international cooperation in science and arms control. Bohr dedicated much of his post-war career to not only advancing scientific research, but also advocating for responsible stewardship of nuclear technology. Upon returning to Denmark, Bohr resumed leadership of the Institute of Theoretical Physics, which he had founded in the 1920s. Under his direction, the institute became a hub for cutting-edge research in quantum mechanics and nuclear physics, attracting young scientists from around the world. Bohr's mentorship and collaborative spirit helped shape a new generation of physicists who would carry forward his legacy. Bohr's scientific work in this period included significant contributions to nuclear fission and fusion research. While he had played a conceptual role during the war, post-war developments allowed him to engage more directly in exploring the fundamental processes powering nuclear reactions. His insights helped refine models of atomic nuclei and contributed to understanding the forces governing their stability and transformations. Beyond pure research, Bohr was deeply invested in promoting the peaceful use of atomic energy. He was an early advocate for what would later become known as atoms for peace, emphasizing that nuclear technology held enormous potential for medical, industrial, and energy applications. He sought to balance enthusiasm for scientific progress with caution about its possible dangers. Bohr also played a pivotal role in shaping international nuclear policy. He was a founding figure in organizations dedicated to fostering global dialogue on nuclear arms control, including advisory roles with the United Nations and the International Atomic Energy Agency. His proposals often emphasized transparency, scientific exchange, and mutual trust as foundations for lasting peace. His philosophy on science and society was rooted in the conviction that scientific knowledge carried ethical responsibilities. Bohr frequently spoke on the importance of scientists engaging with policymakers and the public to ensure that technological advancements serve humanity's best interests. This viewpoint reflected his belief that science was inseparable from the broader social and moral context in which it operated. Despite his advocacy, Bohr was realistic about the challenges ahead. The Cold War and nuclear arms race posed formidable obstacles to disarmament and international cooperation. Nevertheless, he remained hopeful that reasoned dialogue and shared scientific values could eventually bridge political divides. His efforts inspired both scientists and diplomats striving to mitigate nuclear threats. In addition to his policy work, Bohr continued to contribute to fundamental physics through collaboration and theoretical exploration. He participated in discussions about quantum electrodynamics and the emerging field of particle physics. Although his earlier atomic model had been superseded, Bohr's conceptual frameworks continue to influence debates about quantum theory's interpretation and application. Bohr's post-war years were marked by a synthesis of his scientific genius and his humanistic concerns. He embodied the ideal of the scientist as both an innovator and a guardian of ethical responsibility. His legacy during this period extended beyond equations and experiments to encompass the broader mission of ensuring that science remained a force for good in a rapidly changing world. Niels Bohr's intellectual legacy extends far beyond his immediate scientific achievements. He profoundly shaped the evolution of modern physics and the philosophy of science. His work inspired new ways of thinking about the relationship between theory, experiment, and reality, influencing generations of physicists and philosophers alike. The depth and breadth of Bohr's impact can be seen in how foundational concepts of quantum mechanics and scientific inquiry developed throughout the 20th century. Bohr's insistence on the centrality of observation and measurement challenged conventional scientific methodology. He emphasized that the act of measurement does not merely reveal a pre-existing reality, but plays an active role in defining what can be said about a physical system. This viewpoint reframed the classical notion of objectivity and forced scientists to reconsider the meaning of empirical data and theoretical descriptions. One of Bohr's most enduring philosophical contributions was his development of the concept of complementarity, which extended beyond physics into epistemology. Complementarity posits that seemingly contradictory perspectives, such as wave and particle descriptions, can coexist as equally valid yet mutually exclusive ways of understanding phenomena. This insight encouraged a pluralistic approach to scientific problems, acknowledging the limits of any single framework. Bohr's ideas resonated with and influenced contemporary philosophers of science, including Karl Popper and Thomas Kuhn, who explored themes of scientific revolutions, theory change, and the structure of scientific knowledge. His work underscored the notion that scientific theories are not mere representations of reality, but are embedded in a web of concepts, practices, and language that shape how we engage with the world. The Copenhagen School, which Bohr helped establish, became a dominant force in quantum mechanics interpretation, guiding research directions and philosophical debates for decades. The rigorous dialogue and debates fostered by Bohr and his colleagues cultivated a scientific culture that valued deep conceptual analysis alongside mathematical formalism. Bohr's influence also reached the development of quantum information theory and modern approaches to quantum computing. His early emphasis on the role of information, measurement, and uncertainty presaged later explorations into how quantum states can be manipulated and interpreted. Researchers today continue to draw upon Bohr's insights as they push the boundaries of technology and foundational physics. Beyond theory, Bohr's pedagogical style and personal mentorship profoundly shaped the careers of many physicists, including Wolfgang Pauli, Werner Heisenberg, and John Archibald Wheeler. These protégés carried forward Bohr's intellectual ethos, blending rigorous technical expertise with philosophical openness, thus expanding the scope and impact of quantum theory. Bohr also contributed to the understanding of atomic nuclei and particle physics through his collaborative efforts and theoretical proposals. He was instrumental in shaping early nuclear models and exploring the complex interactions that govern subatomic particles, thereby influencing the trajectory of high-energy physics and the quest for a unified theory. Moreover, Bohr's reflections on the limits of human knowledge and the role of language in science resonate with contemporary discussions in cognitive science and the philosophy of language. His recognition that scientific concepts are rooted in human experience and communication challenges simplistic notions of objective knowledge and invites ongoing inquiry into how science constructs meaning. Niels Bohr's contributions to science extended well beyond his groundbreaking theories and philosophical insights. He was also a visionary builder of scientific institutions and a dedicated educator. His commitment to fostering an international scientific community profoundly shaped how physics was researched and taught throughout the 20th century and beyond. One of Bohr's most enduring achievements was the establishment and continual development of the Institute of Theoretical Physics at the University of Copenhagen. Founded in 1921, the institute became a global hub for pioneering research and intellectual exchange. Bohr's leadership style fostered an environment where creativity, collaboration, and rigorous debate flourished, attracting some of the brightest minds in physics. The institute was unique not only for its scientific output, but also for its culture. Bohr encouraged open dialogue between senior scientists and young researchers, breaking down hierarchical barriers common in academia at the time. This approach nurtured innovation and helped to rapidly advance quantum mechanics and related fields, establishing Copenhagen as a world-renowned center of excellence. Bohr's influence extended through his direct mentorship of many physicists who would later become leaders in their own right. His ability to inspire students and colleagues alike was rooted in his openness to new ideas and his philosophical curiosity. Bohr often challenged his students to think critically about the conceptual foundations of physics, urging them to question assumptions and embrace uncertainty. International collaboration was another cornerstone of Bohr's institutional legacy. Recognizing that scientific progress transcended national borders, especially after the devastation of World War II, Bohr actively promoted cross-cultural exchanges. His institute hosted researchers from Europe, America, and beyond, fostering a global network that shared knowledge and ideas despite political tensions. Beyond Copenhagen, Bohr played a significant role in shaping international scientific organizations. He was instrumental in supporting efforts to create forums where scientists could convene to discuss nuclear research and arms control. His vision helped lay the groundwork for institutions such as CERN and the International Atomic Energy Agency, which remain central to global scientific cooperation today. Bohr was also deeply committed to science education at all levels. He believed that a well-informed public was crucial for the responsible development and application of scientific knowledge. He frequently engaged in public lectures and discussions, aiming to demystify complex scientific concepts and convey the importance of scientific inquiry to broader audiences. Moreover, Bohr's educational philosophy emphasized the integration of physics with philosophy and ethics. He encouraged students to appreciate not only the technical aspects of science, but also its broader implications for society and humanity. This holistic approach to education helped cultivate scientists who were intellectually versatile and socially conscious. The structure and ethos of Bohr's institute influenced the design of physics departments worldwide. Many institutions adopted similar models that combined intensive research, graduate education, and interdisciplinary dialogue. Bohr's emphasis on fostering a supportive intellectual community set a standard for academic environments conducive to scientific breakthroughs. Niels Bohr's death in 1962 marked the close of a remarkable chapter in the history of science, but his influence has only grown more profound with time. His multifaceted contributions to physics, philosophy, education, and international cooperation have left an indelible mark on both scientific disciplines and the broader cultural understanding of science's role in society. One of the most visible manifestations of Bohr's enduring legacy is the multitude of honors and memorials dedicated to him worldwide. Institutions, prizes, and even physical landmarks bear his name, symbolizing his pivotal role in shaping modern physics. The Niels Bohr Institute in Copenhagen stands as a living testament to his vision, continuing to lead research in quantum physics and related fields. Bohr's ideas remain foundational in the study and interpretation of quantum mechanics. The principles he championed continue to be taught in physics classrooms globally, and his concept of complementarity still inspires debates within the philosophy of science. Modern research in quantum information theory and quantum computing often revisits Bohr's insights about measurement and uncertainty, illustrating the lasting relevance of his work. The scientific community honors Bohr not only for his discoveries, but also for his distinctive approach to problem-solving, characterized by intellectual openness, interdisciplinary thinking, and a readiness to challenge assumptions. His example encourages scientists to balance technical rigor with philosophical reflection, a duality that remains vital in cutting-edge research. Bohr's legacy extends into the ethical dimensions of science. His foresight about the potential consequences of nuclear technology fostered a dialogue that persists in contemporary discussions about scientific responsibility. His advocacy for transparency, cooperation, and peace continues to resonate in efforts to address global challenges posed by emerging technologies. The story of Bohr's life also serves as an inspiration beyond the scientific community. His courage in the face of political oppression, his commitment to internationalism during turbulent times, and his belief in the unifying power of knowledge embody ideals that transcend disciplines. These qualities have made him a symbol of the humanistic values intertwined with scientific progress. Scholars and biographers have produced extensive literature exploring Bohr's scientific achievements, philosophical views, and personal history. These works highlight the complexity of his character and the richness of his contributions, ensuring that his story remains accessible and relevant for future generations. Bohr's influence is also evident in how science is institutionalized and funded today. His emphasis on collaboration and open exchange helped shape research policies that prioritize international partnerships and multidisciplinary projects. This framework has been crucial in addressing complex scientific questions that require global expertise and resources. Throughout the decades, anniversaries and commemorations of Bohr's birth and death have prompted reflections on his role as a visionary thinker. Conferences, exhibitions, and educational programs dedicated to his life and work reaffirm his status as a towering figure in the history of science. In closing, Niels Bohr's impact is both enduring and evolving. His contributions laid the groundwork for much of modern physics while simultaneously shaping the ethical and philosophical discourse around science. Bohr's legacy is a testament to the power of combining intellectual brilliance with a profound sense of social responsibility, a model that continues to inspire scientists and thinkers worldwide.